Okay, so this is the last lecture, so lab, and well, so.
So this indeed, thank you. The final chapter will be on affine isometric actions. And so the first thing to do is to describe what is action, what are these actions, and there is cohomological framework to study them. But fortunately, if you don't like cohomology, one cohomology will be enough. So we don't need any general cohomological background. So here, today, H will be a real Hilbert space. The space over the reals. And we can look at it as a metric space. So forget the vector space structure, just keep the metric. Then as a metric space, it has a group of isometries. Group of isometries of H. But actually, there is no wild isometry of Hilbert space. Because what do we know? Well, we know the orthogonal transformation, so unitary. I'm saying orthogonal because we are over the reals. So these are linear and they fix the origin. And we know the translations. If we take everything together, we get exactly the full group of isometries. And that's the content of a classical result in geometry of Banach spaces, which is called the Mazur-Ulam theorem. It goes back to the 1930s. And it tells you that every isometry of a real Banach space is affine. And if it's affine, it's the composite of a linear isometry with a translation. Okay. The Mazur-Ulam theorem is a true theorem. But for a Hilbert space, it is nearly trivial. And so let me prove it for Hilbert space. What is special about a Hilbert space is the fact that you have a metric characterization of segments. So if you have 2 points A and B in your Hilbert space, you can go to the segment joining them. And the point is that the segment AB is exactly the set of points C for which you have an equality in the triangle inequality. So you have that the distance from A to B is equal to the distance from A to C plus the distance from C to B. That would not be true in a Banach space like L1 or L infinity. But in L2 it's true, in the space it's true. And since you have a metric characterization of segments, this means that every isometry must map segments to segments, and therefore it must be affine. by a result due to Darboux back in the 1970s. So, okay, so now if we remember that we started with a vector space, so we have 0, and we have the 0 vector, I mean, and this gives us, the Mazur-Golomb theorem immediately gives us a structure theorem for the group of isometries. It tells us that the group of isometries is a semi-direct product of the additive group of H viewed, identified to the group of translation, and here the orthogonal image. And in particular, we have a canonical quotient map on the group of isometries to O of H. And the question I want to address is the following. Suppose that I have an orthogonal representation pi of a group G into O of H. I want to deform this representation into the bigger group isometry of H. And by deform, I mean that I want a map, a homomorphic alpha from G to that bigger group, which makes the diagram correct. So question. How to deform the linear action y into an affine action alpha. So, if I remember this semi-direct decomposition, first, my affine isometries will be expressed as composite of orthogonal transformations with translation. So this means that every affine transformation alpha G, G is a group element, in capital C, will be written pi of GV. So pi of G is the so-called linear part of alpha. Pi of GV plus B of G. And B of G is the translation part. And when you express that alpha is a homomorphism, when you express multiplicativity, you see this is equivalent to one cocycle relation on the translation part. So B satisfies one cocycle relation. B of GH is pi of G, B of H plus B of G. Okay. And now let me use that part of the board to write a dictionary. A dictionary between affine actions and affine isometric actions, one cosine. So first, if we have alpha, which is an action with linear parts phi. Well, as we just saw, this translates into B being a 1 cosine, and so this translates into well, 1 cosine deviation for B. If you take the space of all actions with linear parts phi, so in a sense this is the deformation space of my problem. This corresponds to Z1 equals something which is called Z1 of G pi. So this is the space of 1 cosinus with respect to pi. And observe that that relation here is linear. So that Z1 of G pi is a vector space. Okay, and among now there is a stupid way to deform the representation pi, and this is to conjugate it by a translation. And well, you will have a deformation which has no more information. It just another way to say it is that you made the wrong choice of the origin in your Hilbert space. And so trivial deformations in quotation marks will be conjugates of pi by translation. And if you think a little bit about that, this corresponds to a finite symmetric actions with linear part pi, which have a fixed point. Because, okay, if alpha is conjugated to pi by translation, clearly alpha will have a fixed point. But the converse is also true. If I tell you that alpha is an action with linear part pi, and that alpha has a fixed point, we may use that fixed point to conjugate back to alpha. And on the right-hand side of the dictionary, this corresponds to the space of 1 coboundaries. So B1 of G pi, so this is 1 coboundaries. And this is the set of 1 cosinus B, which are inner in the sense that they are given by a vector in the Hilbert space. There exists a vector B in H such that B of G is pi of GB minus B. A geometric property that an affine isometric action can have is to have bounded orbits. And bounded orbits. And On the one co-cycle side, this translates very, very easily into the fact that B is bounded as a function on G. As a function on G in the Hilbert space. Clearly, if alpha is a fixed point, because we are dealing with isometries, alpha is bounded always. And here it's obvious that if we have such a cohomology, it will be bounded by twice the norm of V, just by defining an equation. But the point is that the converse is true. So this is not completely trivial, but it's quite useful that you have actually an equivalence. So I will come back to that later. And then finally, when you consider all actions up to conjugation by translations, this amounts to consider the first cohomology group, H1 of Z pi, which is by definition a quotient of one cohomology, one cocycle by one cohomology.
Sure. So this is just cohomology. Just the highly pressure related model.
This is function cohomology. This is function cohomology.
But so for example, if the group is simple,
yeah.
Is it true that this is trivial in this case?
If the group is simple, no, this could be not trivial. Okay. Later I will give an example. Well, I will give, for example, I will construct non-trivial cocycles on a cell R. And okay, non-triviality comes from the fact that the representation I can be complicated. And maybe maybe this is what you had in mind, because it is an example. Suppose that pi is the trivial representation of G on H. So this means pi of GV is V. So pi of G is the identity of every group element. Then, there is no cohomology. Pi of GV minus V is 0. So, okay, so we have that H1 of G pi, in this case, is the same as U1 of G pi, but what gives the cocycle relation in this case? Pi of G is the identity. So we see that the cocycle relation just tells that V is a homomorphism from G to the additive group of the Hilbert space. And of course, if G is simple, there is no such homomorphism. Yeah. Or more generally, if G is perfect, so if the abelianization is trivial. Yeah. So now a comment about the equivalence as bounded orbits if and only if alpha is a fixed point. Equivalently, B is bounded if and only if B is a boundary. And the proof is based on the so-called lemma of the center, which is a geometric feature in Hilbert space, which is the following: that if C is a non-empty bounded subset in H, there is a unique crossbow of minimal radius containing B. So, if you look, so this means in the family of all closed balls containing B, there is a minimal object. And it has a name in the literature, it's the circumball.
But you see,
Thanks. And now, if C is invariant under some group of isometries, then the center of the circumball, by uniqueness, is a fixed point. For the same group, the center of the circumball is fixed by that group. And okay, so now if you assume that alpha is a bounded orbit, you apply this observation to one orbit, and you receive the fixed point. Okay. But, okay, you can feel that this is quite useful because, in some sense, proving that something is a coboundary, it's a problem in algebra. While proving that something is bounded is a problem in analysis. So, I mean, you have more tools, and you have both algebra and analysis that can play for you. That's what I mean. So, okay, here's the definition. We say that G locally compact group has property FH, and this stands for fixed points on Hilbert spaces if every isometric and the affine isometric action of G on the Hilbert space has a fixed point. And so we require that every information of direction is a fixed point. So this means this is still equivalent by the dictionary. Is equivalent to require that h1 of g pi is 0 of every orthogonal representation pi, and this is still equivalent to require that every 1 cocycle on G is bounded. So, I mean, these equivalence characterizations we get for free from the dictionary. Not the theorem. So, 1/2 was proved by Genet in 1971, and the other half was proved by his student Delorme in 2 years later, 1953. So, assume G is sigma compact. Countable union of compact sets. Then following an equivalent. First, G has property T. Second, G has property Fh. Well, so this is the link with what we've been doing so far. I think I will have time to give at least one implication, namely, the Kazhdan implication is 2 implies 1. And this is the implication which requires sigma compactness. And what Delorme did was to prove G 1 implies 2, and this does not require sigma compactness. Okay. Yeah. Proof of well, so we are going to work by contrapositive. Assume that G does not have property T. And we are going to, well, okay. G does not have T, so this means there exists some unitary representation pi of G, almost having invariant vectors, but no invariant vectors. Almost having invariant vectors. And the goal is to prove that H1 of G pi is non-zero. Go for it. We don't have to change the representation. And there is a nice argument from functional analysis which will do the job. So we endow the space of the boundaries Z1 of G pi with the topology of uniform convergence And because G is sigma compact, G1 of G pi becomes the spacious space. So, topological vector spaces which is metrizable and complete. And this is really here that we use sigma compactness. And actually, well, with my students, Cornelia and Tessera, we found we were looking for something different, but we found a counterexample for a huge group. Well, actually, it was the real number with a discrete topology. So, you don't want to look at that, do you? but it's locally compact because it's discrete. And something was terribly wrong with in this case with Z1 okay. And in some sense, this was used to construct to prove that for general locally compact books, this equivalence is not true. So you really need sigma compactness. That's what I'm saying. Anyway. So it's a spatial space. And now, consider the following map. And we call it del. From H, well, from H of pi to Z1 G pi. And it maps a vector V to del V. And what is del V? Well, it's just the one cohomology associated with V. So del V of G is pi of GP minus V. So, and let's look at this map. You see, it's a linear operator between the two vector spaces. And what can we say? Well, first, the image of this map is essentially by definition is a space of one cohomology. The second observation is that del is injective. Indeed, if you assume that this function is identically zero, this says that V is a G-invariant vector. But we have an assumption that there is no invariant vector. So, because pi has no non-zero invariant vector. And well, the third observation is actually we already did it on the blackboard, that the norm of this one cohomology is less than twice the norm of V, and as a consequence, del is a continuous operator. And now the claim is that B1 of G pi is not closed in Z1 of G pi. And whenever you find an unclosed subspace in a topological vector space, the quotient cannot be zero. So this implies that H1 power g pi is non-zero. And okay, I agree that this proof is not completely satisfactory in the sense that we will not exhibit any co-cycle witnessing the non-triviality of that space. So it's purely an existence proof. But it's sort of cute because here comes the coup de grâce. So assume by contradiction that d1 of g pi is closed in d1 of g pi. So this means that del is bijective map, continuous bijective map from a Hilbert space to a Fleischer space. So because if it's closed, then it's also Fleischer. So that is then a continuous bijective linear map from Banach space to the Fleischer space. And by the closed graph theorem, so we are in a situation, because the target space is Fleischer, we will apply the closed graph theorem to the effect that the inverse map from B1 to H is continuous. And now we spell out what it means for this map to be continuous. So this means that there exists some constant and some compact set K in G, such that from LDV in the vector space, the norm of V is less than C times the supremum of G in K of pi of GV minus V. Now, assume that V is a unit vector. So, suppose that V equals, the norm of V is 1. Then we get that the supremum over G in K of pi of GV minus V, of pi of GV minus V, is at least 1 over C. And this says that pi does not have almost invariant vectors. And this assumption was not used so far. So this implies that pi does not have invariant vectors. Pardon me? Oh yeah, wait, yeah, sure. Thanks. But not almost. Okay, I think it's almost invariant. Okay, so But at this point, I think that rather than proving the converse, it's probably more interesting for you if I go to some applications. So, so I want to describe applications of the Long-Chardin result in geometry, and I would like to consider the following framework. So, take a metric space, XD. And assume you can you can build a cocycle for the group of isometries of X. So this means assume there exists some representation of the group of X and some cocycle for which you have the following equality, such that for every G in the isometric group, the norm of BG, norm of the cocycle, is a function of the distance. What do I mean by this? Well, so I'm assuming that for some point x naught in x, I can write the norm of B of G as a function of the distance between Gx naught and x naught. And what do I assume about this function capital F? So, it will be a function of non-negative reals to non-negative reals. And I'm just assuming that it's proper in the sense that it goes to infinity and infinity. It is such that limit of t going to plus infinity of f of t is plus infinity. So that's the framework. In that case, any property group G acting isometrically on that metric space XD will have bounded orbits. Indeed, you have acting on isometrically means you have a homomorphism from G to isometries of X. So you compose with the representation pi. This gives you a representation of G with a one cocycle. By property T, that one cocycle must be bounded. So you know that this quotient T is bounded. But by assumption about the function capital F, the distance between Gx naught and x naught must be bounded. So let me spell this out. So G goes to the norm of G is bounded on G, hence the distance between Gx naught and x naught is bounded on G. So this means that the orbit of x naught is bounded, and since we deal with isometries, every orbit is bounded. matrix of V on X. And in good cases, you may go down from bounded orbits to fixed points. Like we did in Hilbert spaces, if you have a lemma of the center, or if you have a body-center construction, then you may go down from a bounded orbit to a fixed point. And I will give two examples which illustrate this principle. So, A. It would be the case of T. So, X as a DE is 3, and the T is a connected graph. Without circuit. Graph which is both connected and simply connected. And of course the interesting case will be infinite trees, where to have a, let's say, fairly large homomorphism. So we consider, for instance, the tree, so the three regular tree. This is typically one of the examples I do in math. And okay, we're going to construct first a representation of the isometric group, and then a cosine. And for this, let me denote by E special the set of oriented edges of X. So by this I mean, well, in a sense it is two copies of the set of edges. Every edge coming is coming with two possible orientations. So you may orient from left to right, or you may orient from right to left. So this means that every edge becomes doubled. And E, so E special denotes the set of oriented edges. And okay, so the Hilbert space I'm going to play with is L2 of E special. And of course, the group of automorphism acts on the situation, and particularly it acts on the Hilbert space by permutations. And so let me give a name to the by permutation representation. Let me call it pi. Now, I'm going to define a map, a two-variable map from V into L2 of oriented edge. So this means that whenever I take two vertices, x and y, in the tree, I want to define the two functions c of xy. Actually, it will be a function with compact support, with finite support, which guarantees that it is L2. But so E is an oriented edge, and C of xy evaluated at E will take the values 0, 1, and minus 1. And it will take the value 0 if E is not on the geodesic xy. So here I'm using for the first time a property of trees, namely that they are uniquely geodesic, in the sense that whenever you have two vertices, you have a unique geodesic path, which I denote by x1. Okay, and this immediately guarantees that my function will have finite support. But now I put the value 1 if E is coherent. I mean, when you move from x to y, you meet the E is oriented in a coherent way. And of course, I will put minus 1 if E is oriented in a non-coherent way. And so I have this function C. And let us study a little bit this function, because it's the one which ultimately will give us the cosiders. First, everything is canonical so far. So this means that this function C is certainly equivalent with respect to the actions of automorphism. So if I apply pi of g to the function C of xy, I will find C of g of x, g of y. And this is for every g in the automorphic group, for every x and y vertices. Second, let us compute L2 norm squared. Well, if we square, we get either 0 or 1. When do we get 1? Exactly when E is an edge on the geodesic. So we get the geodesic distance, d of xy, between x and y, with a factor of 2, because every edge is counted twice, with the two possible orientations. So here we get 2 distance between x and y. And finally, the most interesting relation is the following. C of xy to C of yz is C of xz. So every x, y, and z vertices. And the reason is that, okay, we have 3 points. So they determine a triangle. The triangles in the tree have a very special shape. They are not triangles, they are tripods. So here's the triangle x, y, z. So the 3 sides meet at some point. But now, look at what happens. When we go from x to y, and then from y to z, look at what happens in this branch. Edges which were coherent from x to y become incoherent when you go from y to z. And this means that this branch, the contribution from this branch cancel out. And that's the proof. So contributions on that branch of the cycle excellent. So that's the proof of this relation. And okay, now fix. And now, so far everything was canonical. And now I'm going to do something non-canonical. I'm going to fix a base point. X naught in V. And I will define the cocycle, Vg. This will be C of Gx naught. X naught. Let me check the one cocycle relation. V of Gh is C of Gh X naught X naught. By the third relation, this is the same as C of Gh at X naught Gx naught plus C of Gx naught X naught. So this one is V of G. And the third one, the first one, by the equivalence relation there, is pi of G C of Hx naught X naught. And as we say, the other one is V of G. But now this one is V of H. Pi of G V of H is V of G, as it should be. So, okay, so we have, this means that we have a canonical, well, up to the choice of the base vertex, and if you change your base vertex, this amounts to conjugating by a translation in your Hilbert space. And this is normal, after all, we are dealing with affine Hilbert spaces. So, in an affine Hilbert spaces, choosing the origin is not canonical, so to speak. So we have a one cocycle relation, yeah. So here my function f is square root. So what am I saying? Yes, that's correct. So the framework is realized with pi d, and we have that norm of Vg is root of twice the distance between Jx naught and X naught. And as a consequence, we have that whenever, to answer depending on what you know about PID groups, but the group SL2 of QP it acts very nicely on the P plus 1 regular tree. And it's a simple group. So we constructed a very non-trivial one-plus cycle for on SL2 of QP.
May I ask another question?
Sure.
What does this cocycle tell you about the tree?
About the tree? Not so much, but it tells us a lot about the isometrics. So, no, what I'm saying is that so far we have that a property T group acting on a tree must have bounded orbits. And now this can be combined with the lemma due to Jean-Pierre. But it's a very elementary lemma. So, if G acts on a tree with a bounded orbit. Then G fixes either a vertex or an edge of the tree. And so I said in good cases we can go down to from bounded orbits to fixed point when that's an example of a lemma which allows us to. From a bounded orbit we deduce that either there is a fixed vertex, there is some fixed vertex or some fixed edge. We cannot hope for more than, for instance, okay, assume I take a tree like that and I just mirror symmetrize it through that vertical axis. So I will have an action of Z02 with no fixed vertex but with a fixed edge. So we can ask, we cannot hope for more than either fixed vertex or fixed edge. And the proof is very easy. Okay, look, take the bounded, look at the smallest subtree 1, and this is an edge of 0, and this is a vertex. Okay. And actually, in his book on trees, Serre introduced the so-called property FA. It stands for fixed points on trees, but where fixed les arbres. The book was even if it has been translated into English, it was written in French, right? So, property FA, if every action of G on a tree has fixes either a vertex or an edge, and so what we have proved, the following proposition that property T implies property F. Okay, I think it's a good point to start. So, thank you for staying with me. So here I want to discuss real hyperbolic spaces and convince you that they also fit in the framework that I described at the beginning of the section. So, it be denoted by xn, so n of R, so that will be n-dimensional real hyperbolic space. It is well known that the group of isometries is a simple Lie group of actually up to local isomorphism. It is a classical group ON1. So this is the group of isometries of the quadratic form. Of signature plus 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 minus, so x1 plus x x1 squared plus blah 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 xn squared minus xn plus 1 squared on and rn plus 1. So that's the move. And in real hyperbolic geometry, we have the notion of hyperplane. So a hyperplane in Xn is a totally geodesic manifold of some space which is isometric to xn minus 1. And the idea in the Bohr model is this. So in dimension 2, a hyperplane is nothing but a hyperbolic line. And so what I will need is the notion of half space. So a half space in Xn is one of the two connected components of Xn minus hyperplane. So here I have two half spaces. And let me denote my H, skip H sub n, the set of hyperplanes. And actually it's much more than a set, it's a manifold, because the group, the isometric group acts on Hn and actually it acts transitively. And moreover, with an invariant measure, which has good properties. In particular, it's a Radon measure. It's a measure which is finite on compact subsets. So in the framework that I described in the beginning, I first need a representation of my isometric group, and so pi is the permutation representation of the isometric group of Xn on L2 of the set of hyperplanes with respect to the invariant measure mu. Okay, and then I need cocycle. And to construct the cocycle, I need a little lemma. The lemma is that if you have 2 points in the hyperbolic space, let's say this thing, Oh, yeah. Okay, I need a piece of notation. Let me denote by h of x, with h of x. What is this? It's the set of R spaces containing x. So, this is some open set in H10, but it's a huge open set, and in particular it will have infinite measure. But what the lemma says is what the lemma says is that if you take the symmetric difference between hx and hy. So what's this? It's a set of R spaces which separate x from y. Well, this is relatively compact. So it has compact closure. In H2. And let me give the proof in dimension 2. So, it's enough to see, it's enough to check that the set of lines in X2 intersecting the geodesic arc xy is relatively compact. So let me try to do drawing in the disk model. So I have 2 points, x and y, and I consider all lines, all hyperbolic lines which intersect that closed geodesic arc. I want to show that this set is relatively compact. Now, okay, what is special about dimension 2 is that a line is completely determined by the two endpoints, the 2 points of infinity. Say p minus and p plus. These 2 points in the boundary, and hence, what is the space of lines? Well, the space of lines in X2 is, well, we need to take 2 points on the circle. So you get S1 cross S1, but these 2 points must be distinct. So you must remove the diagonal. And then maybe to take, since we are dealing with unoriented lines, we divide by the action of symmetric 2, and then this is like the fake action. This is really the space of lines, and
which is an obvious open Möbius band.
which is an open Möbius band, correct. And the point is that we want to see that those lines which intersect that arc, the set of those lines is relatively compact. But okay, let's look at the worst case scenario. How can it be not relatively compact? Well, this would mean that we get close to the diagonal. But you see that if we get close to the diagonal, so this means that T plus and T minus are close together, like this. And in this case, if they are close together, the line that they determine will certainly be far from xy, and that's it. So, T plus T minus is close to the diagonal, then T plus T minus are close together. And the line that we determine will not intersect. Okay, of course, in higher dimension it's more complicated, but it's still true. And using this lemma, I may define a two-variable mass from xn plus xn to L2 h and u. So remember what we did in the case of keys. So we had a map from V equals V to V plus A. So here we are doing the same. We are doing playing with the same idea. So we map a pair xy to C of xy. And what is C of xy? Well, it will be the characteristic function of hx. So that's the set of half spaces containing x minus the characteristic function of hy. And the lemma tells us that this difference is a function with compact support. So it's so we really land in the little space. So this is what we find by the lemma. Now, okay, what are the properties of this map? Everything is canonical so far, so it is equivalent with respect to the representation pi. The pi of g C of xy is C of gx dy. Then, trivially, this time, C of xy plus C of yz is C of xz. Here it is completely trivial. And now what is the N2 norm squared of C of xy? Well, this is lambda times the hyperbolic distance between xy for some universal constant lambda only depending on the normalization of the measure v. And this is an interesting fact. So this means basically that you can recover the hyperbolic distance between 2 points by measuring the hyperplanes which intersect the geodesic. This is a classical formula in integral geometry called Crofton formula. So this follows. Crofton formula. To get the distance between 2 points, by measuring the set of hyperplanes separating them. So, originally, the first Kazhdan formula was proved by Kazhdan, I think in 1860 or something like that. And it was for in Euclidean geometry for points in the plane. But if you think about it, it's already something. I mean, it's quite obvious that if you measure all the lines which separate 2 points in the plane, you really measure the distance, the Euclidean distance between these 2 points. So, okay, and this was extended first in Euclidean geometry and then in hyperbolic geometry. But, okay, so here we are. And then we can do exactly what we did in the case of trees to define the cosine. So, like in the case of trees, we define B of G is C of G x naught, And because of the two first relations, this is indeed the cosine for the isometric group of x with values in the computation part. And immediate consequence is that a property T group acting isometrically on a real hyperbolic space will have bounded orbits. And here, we can go down from bounded orbits to fixed points. So, because in Xn, we have the notion of barycenter. Just like in Euclidean geometry. So there is, I mean, if C is a convex set, so meaning geodesically convex, then the barycenter integral over C of phi d volume p. So I mean, such an integral makes sense. So that's the traditional definition of the barycenter in Euclidean geometry. So the same formula makes sense. And as a consequence, if you have a bounded orbit, well, you take the convex hull, take the barycenter, get a fixed point. Alpha on G to the isometric group of X xn is a continuous homomorphism, then alpha of g has a fixed point in xn, and the closure in this group, in the axiomatic group, is compact. Why are they compact? Well, just because point stabilizers are maximal compact subgroups in the axiomatic. Remember. Point stabilizers. Maximal compact. Well, I think it's a good point.
Questions?
What question?
Do they have more classes?
So the camera is not supposed to ask any questions.
Yeah. But of course, well, there is an open question, but I already mentioned it to Carlos, which is that there should be something similar in complex hyperbolic geometry. The point is that if we replace a real hyperbolic space by complex hyperbolic space, we know that this conclusion is true. But we don't have a geometric proof for that. We have the proof is a bit messy, very computational, and so it would be really nice to have to put complex hyperbolic geometry into the geometric framework. But that's